everybody, virtually and non-virtually, to the second midterm review. I'm not anticipating that this will be like super long, probably like an hour to an hour and a half, depending on how much you guys want to practice and things. Real quickly, just like a couple review items that I think are important to note. Some people expressed some slight concern after class today that there was like a lot of stuff. Oh, welcome, Jake. That there was a lot of stuff to know and like a lot of formulas and things. And that is to some extent true. Like this midterm tests on a lot of different concepts. But kind of the key to being successful is recognizing how they're all quite similar in a lot of ways, just kind of riffs on the same ideas. So the main thing that we've added this last week or so has been like continuous distributions, doing lots of stuff with continuous distributions, correlations and things. And so just generally a couple of formulas that are really important to know. Correlation, which is rho, is the covariance of x and y over standard deviation of x times standard deviation of y. Very important to know. Covariance of x and y is equal to x minus mu of x minus mu y. No, not what I want. What am I forgetting here?
Question on correlation.
Yeah.
It's not square root of sigma x, is it? It's just sigma.
Yeah, that's correct. Sorry. Square root of sigma squared. Good catch, Jake. Man, why am I blanking? Somebody fill in covariance here. What am I missing here? I'm just multiplying these things.
Times mu y, or something mu x mu y. I don't know if time is plus or time.
Right.
That is also
like,
it's what we need. Here's what we need. Here's what we need.
Yes.
Yeah.
Mm-hmm. Yeah.
There we go. Okay. I was writing out the other form of expected value x minus mu x, expected value y minus mu y. But this is the better formula.
Quick question.
Yeah.
Rho, is that the same or different from the correlation coefficient?
So those are one and the same.
Okay.
Rho is the correlation coefficient. Rho will always be between -1 and 1. Dr. Price was mentioning in class today that we're dividing by these standard deviations in order to take out the units. What he meant by that is that we're standardizing it. So we're putting it on a scale from -1 to 1 is what we're doing by taking out the standard deviations. So rho will always be between -1 and 1. If you calculate a correlation that is outside of those bounds, less than -1 or greater than 1, you've done something wrong and you need to go back in and work on it again. So these are two very important new formulas that we have. Other important things to remember generally, our good old friend Bayes' law, always kicking. And the way that we're kind of dealing with this now is like f of x equals little x given that y equals little y, which is the joint distribution over the marginal distribution of y at the given point. So these are identical formulas. They're saying the exact same thing. The joint distribution of x and y is the intersection of x and y. So these are the exact same idea. And then the probability of B in the first one is represented by the marginal distribution of y. The marginal distribution of y is giving the probability of y at all points. And so if we just plug in our given y in the marginal distribution of y, we get its probability, which is the same as above. Next thing, estimators. Seem really spooky, a lot of Greek letters going on, nobody knows what's happening. An estimator, by definition, is just something, a formula or some equation that we have to estimate some factoid about our population. So it could be to estimate mu, could be to estimate the standard deviation or the variance, could be to estimate the skew, which we won't talk about in this class, but it's just some equation to estimate a value. The way that we find bias, the bias of some estimator, which I'll call theta hat, is equal to the expected value of theta hat minus the thing that we're estimating, which is theta in this case. So bias of the estimator minus the thing that it estimates. If your thing is estimating mu, then you subtract mu. If your thing is estimating sigma squared, you subtract sigma squared. And if this equals 0, then your estimator's unbiased. Huzzah. Efficiency is a comparative statistic that we get by taking the variance of our estimator. No value in and of itself is efficient. We can't just like take the variance of an estimator and say, yep, that's for sure efficient. Efficiency is a comparative value. So we always need to compare the efficiency of one statistic or of one estimator to another. And then there's consistency, which is if the bias of your estimator and the variance of your estimator go to 0 as n goes to infinity, then it's consistent. So what this will look like if you're like asked a question about consistency, typically you'll calculate, if for something to be consistent, the bias either needs to be 0 or it needs to be getting divided by n. And the efficiency, the variance will also be getting divided by n. Efficiency or variance will never be 0. And so for it to be consistent, it needs to be getting divided by n. Any questions on that kind of general stuff, general review?
Quick question about efficiency. When you're comparing two variances, you're comparing how biased each one is?
So you're comparing their variances.
Okay.
So
in terms of like which one's bigger?
Yeah, exactly. So absolute size. There was a question in one of the homeworks a little bit ago that gave you two estimators, one x bar that weighted everything evenly. It said it was equal to 1/3 x1 plus 1/3 x2 plus 1/3 x3. And then it gave you another estimator that it, I think, called like mu hat or something, that it said was 1/2 x1 plus 1/4 x2 plus 1/4 x3, and it asked you to compare the two, right? And so the bias of both of these is 0. If you find the bias, if you take the expected values. If you find the variance of these two, the variance of x bar is 1/9 x1, 1/9 sigma squared plus 1/9 sigma squared plus 1/9 sigma squared. The way I got to this was I said, okay, what's the variance of 1/3 x1? In order to find this, I can pull out my constant 1/3 and square it, which becomes 1/9. And then the variance of x1 is sigma squared. The variance of anything from a data set is the variance of the data set, right? If that makes any intuitive sense. So anytime you see the variance of x1 or the variance of x sub I or something, it will be, sigma squared. Likewise, if you see the expected value of x1 or x sub I, it will be mu. The expected value of any individual number from a data set is the average of the data set. So this variance, the variance of x bar, ends up being, if we add all these up, 1/3 sigma squared. If we do the variance of mu hat, I won't do it right now, but I think it comes out to 3/8 sigma squared. 3/8 is approximately 0.365, and a third is 0.33. So this is more efficient because it's smaller. There's a smaller variance.
Gotcha, thank you.
All right. There are some practice questions that we're going to go over. Before we go over any of those, are there any kind of general questions, lingering questions from class or from the homework that you guys think would be useful to go over?
Along those lines, for exam 2, like what sections are we covering? Like I'm assuming from SMAs back to, I don't know.
I'm trying to think what we did what the last thing was covered on exam 1.
I think it starts at correlation for us.
Okay.
And then,
So I think that'd be section 7. But then again, like marginal distribution could also, like that comes from the last one.
Yeah, but it
that
would
could
definitely
be thrown
be
in for
involved.
like, was that a covariance question?
yeah. Let's see. So yeah, it's going to cover, we're going to be covering anything having to do with correlation, density functions generally, some early like z-table, normal distribution, uniform distribution stuff, estimators, and that should be most of it.
Are you going to talk about today going from the PDF to the CDF or from the CDF to the PDF?
We'll mention that a little bit. Does anybody know off the top of their head, how do we get from a PDF to a CDF?
I think you
Find the
integrate it.
Find the antiderivative, you integrate the PDF,
Or derive the CDF to get to.
or you can take the derivative of the CDF to get to the PDF. Correct.
And it's over the values of X? Or is there, when you do a PDF, is there just one variable?
I mean, you can, like a joint density function is a PDF with 2 variables.
Okay.
So, so if you were to find the CDF of that, you would double integrate it.
Will we have to go from the CDF to the PDF of a joint?
No.
Okay, because I think we'll have to do that.
Yeah.
Yeah, that's what.
Yeah, I would not. Yeah, multiple variate differentiation is a little bit beyond the class. Okay, so one other principle generally, real quickly. If you have 2 normally distributed functions, or not functions, but, well, yeah, functions or distributions, let's call them z and y. Z is normally distributed, y is normally distributed. First number in the parentheses is the mu, or the average of the data set. So say 5 for z and 10 for y. And then the second number is the variance. 50 and 500. Man, y varies a lot. So if we add these 2 up, if we want to create a new normal distribution, call it x, that is a combination of z and y. If we add together two normal distributions, the result will be a normal distribution. And the resulting normal distribution's mean will be the mu's added from the previous two and the variances added from the previous two.
We're good to just add them, maybe do anything else?
Yep, you can just straight add them.
I'll make it way more complicated now.
But that's if they're independent, or,
Normal.
This is
Just
just if they're
anything?
normally distributed.
okay.
This can get a little bit more tricky if we do other things. If I subtract y from z, actually I'm going to subtract, I'm going to make some alterations to our variables here. I'm going to say now, I'm just going to change z's mean to be 20. So if I subtract z from y in order to get this new normal distribution x, our mean will be the difference between the two, so just z minus y. But then our variance is going to be still their variance added.
Don't you
And
get the covariance?
2 times the covariance.
this is where Annie's question previously does come up to be important. It is important that they're independent.
But this is only when it's subtracting.
Yes.
Oh, okay.
This is only when they're subtracting. But this is where it is important that they're independent. Because if they weren't independent, there would be another term, a covariance term. So what's happening here is I'm saying, okay, variance of z minus y is equal to the variance of z minus the variance of y plus 2 times the covariance of z and y, right? Or actually, yeah. So I know that, y is negative here, and so we might be tempted to subtract the variance of y from z. But if we remember our rules of how we find variances of things like this, we pull out the constants, right, and we square them. So z has a 1 sitting in front of it. Pull that out, square it, it's just 1. Y has a negative 1 sitting in front of it. So we pull out the negative 1, and we square negative 1. Well, negative 1 squared is positive 1. So that's why we add them together. And then because they're independent in this case, we don't need to worry about a covariance term. Because they're independent, their covariance is 0, and thus this term goes to 0. If they were if they did covary, like today, an example in class with the rainfall, he told you that they were correlated, the first month and the second month. And so when you did this step of finding the variance of the new combined distribution, you had to do something with this term, right? If they're independent though, it just goes to 0. If they aren't independent, then it's 2 times any coefficients that could be hanging out in front of these, and then their covariance. Jake.
If it doesn't give us a correlation, or do we just assume they're independent? Or let's say they're independent?
It will say they're independent. If it doesn't say they're independent and it gives you no way to find the covariance, like it doesn't give you correlation or it doesn't give you, like numbers from the distributions to be able to calculate a covariance with, then I would assume that it's
Just
independent.
give up.
But it will say either independent or it will give you a
Should I
relationship.
make a note? Assuming these are independent.
You could do that. You could make an, assuming these are independent, and then if not, then
Then I'll cry.
So
Yeah.
I have a question, and it might be stupid,
okay.
but why, when you do z minus y, you have to do the covariance, like you have to include that in when you find the, like whatever that is.
Mhm.
But then when you add them, you don't have to include it.
You do when you add them as well.
Okay.
I was just kind of implicitly doing these both as if they were independent,
Okay, right.
which was a
So-
poor assumption.
But
in
anything
poor
that is
communication.
like adding or subtracting, it would involve
Yeah.
the like 2 times the covariance.
Yep, there is a
Okay,
covariance
sounds
term in all of those. Just if they're independent, that term is 0.
Okay.
Okay. So posted on the Learning Suite, I've created a new page entitled Midterm Reviews. I'd recommend, if you have a computer with you at the moment, to pull out Learning Suite and to go to that page. Posted under that midterm review page, it says Midterm 2, and there's a Midterm 2 document that you can pull up. So we're going to look at some of these questions that I have, some practice questions, and then we might take a look at the practice exam for a minute as well. I wrote this document last term, and so there's like one true false I think that you guys haven't learned the material for yet, so we won't need to worry about that one. But
Which one is it?
which question is that?
Yeah.
Question 3 is a stated question, so don't need to worry about that right now. Let me know when you guys have that pulled up. Annie's good. Annie's set. Jake is set. Okay. I mainly have you pull it up just so I don't need to like write on the board what these true-false questions are, but we're going to start with some true-false. Tell me if this is true or false. To find the probability that a variable x will fall between two numbers a and b, integrate the cumulative distribution function of x from a to b.
Sounds true to me.
We're getting a sounds true from Chris.
Yeah.
Do we have any agreement or disagreement from the peanut gallery?
Which number was that one?
Number
Number
1.
1.
Yes, true.
Jake is agreeing. True.
I say it was what?
Oh, hold
Annie
on.
agrees.
No, false. I said
Oh,
false.
Jake is now in the contra party.
That's making me question.
Jake, why do you think it's false?
Because it says to integrate the cumulative
When you really
distribution
should be
function. It should be the what does PDF stand for? Probability density.
Probability density function. Yeah, exactly. This is false.
They got me.
The cumulative distribution function is the integral of the PDF, and we have to integrate the PDF in order to find this. If you wanted to find the probability that a variable x falls between those two numbers a and b using the CDF, you would just plug in a and b into the CDF.
That's like a class, like my finance class. Should we just do stuff like that? Just have definitions, we'll just like switch one word.
Yeah.
Like true or not.
Yeah.
Like yes or no, and then it should switch to like no or yes. It's
Yeah.
simple.
Pretty classic.
So you read it and be like, yeah, but it's just the wrong word.
Okay, question 2. If x and y are independent, uniformly distributed random variables, then the joint density function fxy is constant over its domain.
True.
Got it true? Matt's nodding his head,
I think it's true.
feeling it's true. This is true. We did a question very similar to this in class today, except for it was a bit more advanced. It asked, if this distribution is uniform over 0 to 2, and this other one is uniform from 5 to 10, is its height constant over its domain? It's correct. Okay, question 3 is the stated question. We'll skip that.
Should we guess?
You could guess if you really want to.
50-50.
I'm going false.
We've got a false from Chris.
I'm
Haven't read
going
it.
true.
Got a true from Annie.
I didn't even look at it.
What do you vote,
True.
Jake? Got a true from Jake.
False.
Is it
And a
true?
false from Matt. We're split 50-50. It's false.
Oh, dang it. I was going to say we should put something on.
Oh, flip.
What was that?
My phone that's recording. My apologies, anybody who's watching this.
Probably my fault. I think about to do.
Come on, Jake.
You just woke him up.
Okay. Question 4, last of the true-false on this little document. Assuming x is normally distributed, x times any constant will also be normally distributed.
minus any constant? Wouldn't it just stretch it out? Like if it's like normally like wider, when you times it by constant, wouldn't it just like,
Nope,
keep
it
it
stays normal, I think, right? I mean,
But it's
some-
normal, but it transforms it, like it doesn't stretch.
So
But that's could still be
Yeah,
normal.
so
It's
this is
normal,
true.
so sure,
It's
sorry.
normal.
here in truths,
Yeah.
here in truths,
Guessing?
it is true. You're right. It will transform it. It will
it's
change
still
it, but it'll just make all the values bigger by 3, or whatever the constant is. So yeah, it will stay normally distributed.
I have a question about number 2.
Okay.
If X and Y are not independent, how does that change the, like,
The situation, the
situation?
vibe,
The vibe,
if you will.
Yeah. How do I
Um,
read the room?
So in order to answer this question, we're basing this around one of our definitions of independence, which is that the joint distribution function is equal to the marginal distribution functions multiplied.
Mhm.
If they're independent, this is true.
Okay.
And so, if they were, well, I mean, if they were not independent but both uniform,
Mm-hmm. But like.
no, because if say y happened, more often when x also occurred, like originally y could have been uniform, but now that it's being affected by x, it
It's
might
not
no
necessarily
longer be uniform.
anymore.
Yeah.
Okay.
Yeah.
By the way, that fx, parentheses x, that's always indicative of like the marginal distribution.
Yeah, F, like
I
F
actually don't know how to say
subscript
that, but
X,
yeah.
X. This is our notation for the marginal distribution of X. Yeah. All right, now we've got the first long answer. I apologize, when I wrote this document, I did not know math type. Dr. Price would be very disappointed in me. But I also apologize that this is a 1, 2, 3, 4, 5, 6, 7, 8 part question. A through H, you love to see it, really letting my inner Dr. Curl take over. But he's here in spirit. So it gives us this joint distribution function, which I'll write out for greater clarity. So it gives us this. And then it gives us a bunch of parts of questions. So I'm going to give you guys some time to ponder, to calculate, to do what you've got to do, and then we'll go over it a bit more afterwards. But first, you're going to search for K, and then find some marginal distributions, some expected values, all the way down to correlation. So I'll give you guys some time to start working on it, and then after I give you guys a couple minutes, I'm going to start working it out on the board. I'm not going to talk. I'm not going to do anything. I'm just going to work it out so that you guys can finish the question as well, and then we'll talk through it.
Can you check if my answer is correct?
Come on, Jake. We're going to be
okay,
going.
I'll wait. I just don't want to freak out. I'll freak out. I'll just sweat it out.
You'll sweat it out, Jake. Plus, I'll write the answer to part A up in like 30 seconds. So
That's what I was wondering. Wait, are we doing All of them right now?
Crank them. Just start
Oh, okay.
grinding.
Oh, okay.
Start grinding through it.
I just don't want to do them all if that A was wrong, because that would ruin everything.
That would be very awkward. But it's a constant, so it would be pretty easy to fix.
Oh, but it would just make me so sad.
By show of hands, who's through part D?
I'm about to finish D.
Okay.
So,
We'll take a pause at part D so that we can talk through this, and then I can erase the board and start doing the later parts.
So proceed real quick, did you have to find the marginal for y as well?
Yeah.
Okay.
Oh. So I made some critical mistakes. Oh wait, no. I
But they're
didn't.
the same.
No, I didn't make any mistakes. I did on part D.
Okay, we ready to talk about parts A through D?
Yes.
All right, cool. So part A, to find the constant k, we need to set the double integral of our joint PDF equal to 1 and solve it out. So we set up the integral like this. It doesn't matter if you first integrate with respect to x or with respect to y. In this case, they have the same bounds. You'll just want to make sure that you match up the bounds with the variable that you're integrating with. So if, say, y was on 0 to 1, but x was on 0 to 2, and I integrated from 0 to 1 with respect to x, that would be bad, because I would be integrating on y's bounds with respect to x. Don't want to do that. Very bad. In this case, though, they have the same bounds, so it's going to turn out the same either way. I integrated with respect to x first. Once you do that, you're left with the same thing, but with no x, and this term is being divided by 2. You integrate with respect to y, and you set k by itself. You end up with 4. Any questions on how we got there on part A?
Is there a specific reason, like, we know to go to 1?
Yeah, so we know that all probabilities have to add up to 100%,
Okay.
right? We have to cover everything, and so if this is a valid joint density function, it will sum to 100%. All right, part B, the marginal distribution of x. So the way we find the marginal distribution of a function using our joint distribution is we essentially just need to get rid of whatever variable we don't want, right? So in this case, we've got a y that we don't want. We just want x's. And so how do we get rid of the y's? We integrate with respect to y on y's bounds. And so we're looking for x. Sometimes it's a little confusing for people. We're looking for the marginal distribution of x, and yet we're integrating with respect to y. But once you do a couple of these, you realize, like, oh, if I integrated with respect to x, I wouldn't have any x's. And then, that's not going to be very helpful. So we set up the joint density function, this time with our constant k plugged in as 4. We integrate with respect to x. We end up with 2 minus 2x. On part C, I kind of skipped a step a little bit. Normally, to check for independence using density functions, we would multiply together our marginal densities, marginal density of x and marginal density of y. The idea being that if it ends up being the same as the joint density function, then they are independent. In this case, I looked at this function and I said to myself, to quote Curl, self, x and y are the exact same in this scenario. By symmetry, I know that their marginal distributions are going to look identical, right? Doesn't matter if I integrate this with respect to x or to y, it's going to end up being the same thing. And so instead of doing this process again, but for y, I just said, okay, this is going to be the same equation, just with a y instead of an x. Totally fine to not recognize that and to integrate with respect to y. In most cases, they will not be the same, and so you'll have to find the marginal distribution of y anyway. But we multiply them together, we FOIL them out, we see that the result is not the same as our original function, so we can determine that they're not independent. Moving on to part D, we're asked to find the expected value of x. The way that we find an expected value using joint density functions and marginal density functions is we multiply x by, well, we multiply the variable by its marginal density function, and then we integrate that along its bounds. And so kind of the way this connects with previous units is we've said, okay, expected value is the sum of all of the outcomes multiplied by their probabilities, right? That's the expected value, typically. That's what we're doing here. We're taking all the values of x and we're multiplying them by their probabilities, which is the marginal distribution, right? And so we multiply together the probabilities and all the x values, and then we integrate that from 0 to 1. And so we integrate this with respect to x, we end up with a third. This question's a bit more conceptually difficult. Do we have any questions on, well, any of these parts, but particularly D or C?
It's like that middle equation. It's 2 minus 2x, maybe like one above it. See if
This
x, yeah, because it's, and then the marginal.
Yep.
Is there any reason why we wouldn't put in, I guess, is 2 minus k x y, that's f of x and y, right?
Yeah.
So we're only looking for the x.
Yep.
Because it's the marginal distribution of x.
Exactly. So since we're looking for the expected value of x, we don't want any y's in there kind of goofing with things. And so we'll just use the marginal distribution. If they ask you for the expected value of y, use the marginal distribution function of y multiplied by y.
Perfect.
Sweet. I'll let you guys get going then on part E. And then we'll maybe break at part G, or just let you go all the way to correlation. This is low-key kind of a test for me too. I'm like, man, gotta make sure I do this right.
For E, do I want to do the derivative of?
Yeah.
Derivative? Isn't this the derivative of the P? This is the PDF, right? No,
That's the joint density
joint
function.
density function. PDF being the marginal,
Because I'm used to like just finding.
so I can do the derivative. It's just that, so there it is, right?
Is just something,
Or no?
it'll give you something.
Shit, I don't know, Jake.
Plug in
I don't know.
X
You do know,
values
Dan.
In order to
The
find
problem is
the
I don't know.
integral of the like x.
Yeah, this makes sense.
Did it make sense?
Yeah, the PDF.
Yeah, it's like, yeah,
No.
just set it up as if you're gonna solve for it, but yeah, just basically find the derivative, so it leaves you like, or not the derivative, find the integral, so, yeah, so it leaves you.
Wait, I have no idea.
Still got it, baby.
Why'd you do something crazy? Why'd you do dy and then dx? That's wild. I just hate you.
I like to spice things up occasionally.
But now I have to like do mental gymnastics to figure out where I went wrong. Not really, actually. Oh, that's what I did wrong.
How's it going, girl?
So exciting. Yeah, bye.
Oh, I got
Yes.
positive 1/18.
Mmm.
So I don't know what I did wrong.
You're close.
You didn't do correlation yet, did you?
I've not done correlation yet. We'll take a brief pause and then maybe do correlation together. 'Cause it should be.
Wait, no, I just did it.
Okay, where are we at? Are we down to G?
Yeah, I'm working.
I'm almost
G.
done with G.
Okay.
Stupid math error. Always getting. I integrated this. The second part of the double integral, I just did x squared, I did 1/2.
Gets them every time.
It's true, I really got it.
As not fun as Calc 2 has been this term, it has made me much better at integrating.
Are you in Calc 2 right now?
Yeah,
Oh, it's gotta be rough.
it's not the funnest.
Hopefully I get into the strategy program, otherwise my whole today applied to Bain and Mackenzie. So
Oh,
if I
really?
get in, then it just forget it, I guess. I was gonna apply to the BCG summer internship, but it closed yesterday. I didn't realize that it closed yesterday, so instead I just applied to Bain and Mackenzie.
Yeah.
These are internships.
I've got some contacts at Bain and at Cicero. If you want to talk to anybody.
I don't even know any other consulting firms we've had as BCG, Mackenzie, and Bain, so I probably should find some other ones.
Cicero is a smaller firm out of Salt Lake.
See, that would be nice, because Bain and Mackenzie both don't have offices in Salt Lake.
Yeah.
Neither does BCG, but.
Cicero is it's smaller, but it's a very respected group, and I know some of their consultants.
I put my top 3 destinations for Mackenzie. I think I did Chicago, Dallas, and Washington, D.C.
Nice.
And for Bain, I did Dallas, Chicago, New York City.
There we go.
So that way, all of the pay that they'll give me, I can just spend on rent.
Yep, spend it all on your apartment. Dallas wouldn't be too bad.
No. I mean, it pays well. The Bain summer internship's like 10 weeks, it's like $8,000 a month.
Yeah.
But if you're in New York City, it's probably just barely surviving.
Yeah. All right, let's talk about these real quick. So, E, E is a bit more of a conceptual question. So it asks you to find the CDF of x and then set up an equation to find the median value of x. So the CDF of x is the antiderivative of its marginal distribution. Its marginal distribution is essentially its PDF, and so we integrate that sucker and we get a CDF. So the CDF, conceptually, what it's doing is it's adding up all the probabilities of x as it goes, right? It looks like something like this, where this is y equals 0 and this is y equals 1. And so if we want to find a percentile, where a certain percentile is at of a CDF, well, all it's doing is kind of gobbling up probabilities as it goes. And so, like, whatever number we put into the PDF or into the CDF, it's going to spit out a percentile. It's going to tell us how, what amount of the probabilities have been added up to that point, to the point that you've put in. And so if we want to solve to find what value of x gives us the 50th percentile, we just need to set the CDF equal to 50%, 0.5. And if we solve this for x, it's going to give us what x value yields us that, right? Jake.
2 questions.
Yes.
When you do the CDF, you just do the general integral, not over a range.
Yeah.
Then if that's the case, don't you need a constant of integration?
So we do have a constant of integration here, but since like the CDF does exist on a bounds and we're always going to, integrate it, we're always going to plug stuff into it, the C's are going to cancel out. And so I just don't worry about them. Any other questions on E? Moving right along to F, which asks us to calculate the standard deviation of x. So we knew from a previous part that the expected value of x is a third. The way that we calculate variance, of course, is by doing the expected value of all x values squared minus mu of x squared, right? That's our classic variance formula. And so just like how we multiplied x by all of its probabilities to find the expected value in a previous part, now we're going to multiply all of the probabilities by x squared, just like we would do with, discrete numbers back in the day before we got PDFs and CDFs and things. So we multiply our marginal distribution of x by x squared, and then we integrate that along its bounds of 0 to 1. That results in 1/6 is what you get from that. But that's not our final answer. We need to subtract mu of x squared from that to get our variance. So we square our expected value of x, which was a third, we get a 9th. Subtract those two from each other and you get 1/18. We're still not done yet. That's the variance of x, but we want the standard deviation. And so we need to take the square root of 1/18 in order to get that standard deviation. Questions on that part? Feeling good? Feeling loose? Feeling warmed up? Covariance. So again, we've got the same type idea of what we were doing before PDFs, multiplying, x and y by their probabilities. We multiply x and y by their probabilities, which is the joint distribution of x and y. So we multiply these through, and then we have to double integrate the joint PDF. I started with y, which Jake ridiculed me for unfairly.
Unfairly, that's crazy.
Completely unfounded. But so we then integrate with respect to both variables. When you do that, you end up with 1/18. But again, we're not done. We need to subtract from the expected value of x and y mu x times mu y. Mu x and mu y are both a third. We found that x was a third earlier. You could have solved out the marginal distribution of y to find the expected value of y, or you could have noted, as we did earlier, that their marginal distributions are the exact same, just one has an x and the other has a y, and thus their expected values will also be the exact same. So both of their expected values are a third. 1/18 minus 1/3 times 1/3, 1/9, you end up with negative 1/18. Yes, sir.
Quick, somewhat unrelated question about symmetry. That's
Yeah.
related to the balance, right? Because X and Y both 0 to 1. That's
So-
what causes the symmetry.
So it's related both to the bounds and to the function itself. Like, if, let's just say, for the sake of argument, that X and Y were both bounded by 0 and 1, but we had X squared,
Yeah.
And why
2y
not?
minus kx.
then
it's
it would be.
dependent on both. They both have to match up.
They both have to match. Both their bounds have to match, and they need to, be in the same position in the
Somewhat
equation.
interchangeable.
Have the same, be to the same degree, and be multiplying by each other. Cool. Any questions on G? Then it's correlation time, as they say, which many people say. I hear many people say that around. I'm very cool, very hip with the kids.
Keep bumping your table.
So correlation is equal to the covariance of X and Y over their standard deviations multiplied, right? We just found the covariance as negative 1/18. We previously found the standard deviation of X to be the square root of 1/18. We could also hunt for the standard deviation of Y, but as we've noted about the symmetry of the two, it will also be 1/18. I'm going to rewrite this ever so slightly to say 1/18 to the half power, 1/18 to the half power. You can see that these just combine to be 1/18, right?
Yeah.
We get negative 1/18 over a positive 1/18, which equals negative 1. They are perfectly inversely correlated.
Beautiful.
Amazing.
Does that ever happen in anything?
If you are doing, say, your data project and you find that two of your variables are perfectly correlated or inversely correlated, it means that you've probably picked two things that are like inherently, like tied together. For example, let's say like your two variables are like if you're married and if you have a marriage license, like, yeah, they're going to be perfectly correlated because they're the same thing, Typically, if you get a number like this or very close to it and your variables aren't like the exact same thing, it means something's gone wrong. There's really nothing that's this correlated.
Until I find out.
Until you find out,
Yeah.
You can find like silly things. You guys looked at the spurious correlation website,
Yeah.
right? So like you can hunt out things that happen to have the same like shaped curves and but yeah. Cool. That completes the meat of the long answer. We have one other long answer question to go through. It's significantly shorter, significantly faster. It has to do with normal distributions. So I'll let you guys get started on that. You're going to need a Z table to complete this question. So I would grab one out if you've got a physical copy or pull up some digital version of it. That would also be excellent. Dr. Price nearly did it to all of you by not providing one on the test, which would have been epic.
That would have been terrible. Because I would have been like, I'm pretty sure I need a table, but they didn't give me one. So maybe I don't need a table. That would have just been nice.
You want to do number 6?
Yeah, go ahead and start going through number 6. I've not written any of the answers on the board because I didn't write down any of the z-scores, so we'll do that as we go. Can I do the Dr. Price thing? Why
If you go
Interesting. Please don't.
I want like nothing written down, and you'll tell me how interesting it is. Which is true, I guess.
I mean, that is pretty interesting.
Yeah.
All right. What's the z-score? Anybody calculate it?
Yeah, it's 0.19.
0.19, you say?
That's what I say.
Those are the words that you say? Okay, so what percentage does this equate to? Wait,
I got 1.19.
1.19? That feels like it should be closer.
Oh no, what has happened?
So Annie, what did you calculate? What's your percentage?
0.117.
That sounds excellent to me.
Wait, I'm so scared.
0.11. Oh,
Did I do
Yeah.
something wrong? 775. Oh wait, why are you doing the square root of 100?
you're not.
Is that what it is? That's what you're supposed to, I just messed
Hold
that
on,
up.
no, wait.
That's not.
No, that's
because
false.
the
That is
standard
false. It
deviation
is already
100.
standard
Yeah,
deviation.
that's what I thought.
That's my bad. 100%. Take full credit, full responsibility.
Oh, but the answer is still 0.1.
Yeah, that is
I
correct.
said-
I just wrote it up on the board
I
wrong.
still did it wrong. I don't know how I must have missed a 0.
All right, what did we get for the z-score on part B?
0.56.
0.56. Are we sure about that?
Well, or it would be 1 minus point, or negative 0.56. I guess.
Negative
Really,
0.56.
Yeah. yeah.
Negative 0.56. Why is it negative?
Because it's negative.
It's below
it's
the
below
mean,
the
right?
mean.
It's below the mean. So what percentage does this equate to?
0.2877.
28.77%.
Whoa, hold up. Question.
Yes.
1.9 z-score.
1.19.
Oh, 1.19. You don't need to do 1 minus that.
Yeah,
Because it's
that's
asking
what
for less. Is it, if it's
That's
asking for less,
what I was
then,
thinking as well.
do you need to do 1?
Well, so it's asking what percentage of American drivers use more than 775.
But this
gallons.
is for
Oh,
the next
use
one.
more. I'm sorry, I read that part wrong. And then, the
And then
next
for
one
part
uses
B,
less.
what uses less? Yeah, what percentage uses less?
So 1 minus
Would it be 1 minus
0.28.
28.2877?
No, because, so I mean, if we look at like the distribution here, right? This is the mean, this is 656. 650 or 600 lies somewhere like right there,
Mhm.
right?
Yeah.
So I mean, just conceptually, if you were on a test and you were asking yourself, okay, do I do 1 minus or do I do just the thing that I got? Well, looking at this, the people who use less sit right here on the graph, right? So to me, eyeballing it, does this look more like 28% or does this look more like 72%?
Oh.
28%, right? But then also, so the way your table's formatted.
Because that's why I thought, because it's like, I thought that this would be all of that.
So the way your table's formatted is it just shows the positive z-scores. It just shows the positive z-scores and then it tells you what lies above.
Oh, so
And so if you're using a negative one, it's telling you what lies below.
I gotcha.
Oh. Okay.
Can you do that with all of them? Wait, just kidding, forget it. Don't even, pretend like I didn't ask that.
Okay. sounds
Cool.
good.
It is wiped from my mind.
Now try it out.
Okay, part C. What amount of gas would I have to use in a year to be in the 99th percentile of American drivers? What's the procedure here? What do I do first?
Well,
Jacob?
You need to do 0.99, because that's the percentile equals. It's just reversing what you did earlier.
So I just do 0.99 equals
X minus the average 656 over 100.
Jake, this is slightly wrong.
Oh, shoot.
because you have to find the z-score that.
Gotta find the
correlates
z-score.
With 0.99.
This always gives you a z-score.
So I need to go get the 0.99.
So we gotta find the z-score that is equal to 0.99.
Which would be 0.01.
So this,
Would it be
It would be 0.10.
0.32?
2.32.
Yeah.
Wait, 2.2?
Or possibly 2.33.
So one of these two.
Yeah.
Oh, wait, because it's 01. 2.1.
Let's see which one I used when I wrote this. So we'll plug in 2.32. Solve this out, solve for x, multiply by 100, 232 equals x minus 656. We add over the 656, and what do we get?
888.
888. Looks like I used this one in the answer key. You hate to see it, no.
Well, it is
Either of those
closer.
answers would work.
It is closer.
Either of those answers would work. I'm not going to get too angry if you pick.
Just a little.
Oh, how embarrassing.
Just a little angry.
Little-
I'll just.
little piece.
I might get a little red in the face.
How embarrassing. My team won this question in the review today, and then I've messed it up right now.
Truly devastating, Jake, is all I could say.
Taking off that homework group. I can do it all by myself.
All right, so this finishes this little review paper that I have. I do want to look really quickly at one of the questions on Dr. Price's practice test. And then I'll open it up as well if you guys have any questions on any of the practice test questions or anything generally that that is on your mind. So I really quickly want to look at just the first true false in Dr. Price's practice exam. So you guys can pull it up. As you're pulling it up, it says if x and y are random variables with a correlation of rho xy, then the correlation 2xy is equal to 2 rho xy. So
Illegal.
very illegal. So correlation xy equals rho xy. We want to look at the correlation of 2x and y and see what that equals. And it is postulating that it should equal 2 rho xy.
Okay.
So what do we know about correlation?
We know that it is equal to covariance over sigma x times sigma y.
Exceedingly true is what this is. So if we want to look at the correlation of 2x and y, well, first I'm going to rewrite this slightly. I'm going to rewrite this to be the covariance of x and y over the square root of the variances. So pretty much the same thing, you know. So if we look at the correlation of 2x and y, we need to replace x with 2x everywhere that, you know, x pops up, right? And so we're gonna have a covariance with 2x in it. And we're going to have, and I'm actually gonna rewrite this as well. I'm gonna say variance of x and variance of y. Then we're gonna have the square root of the variance of 2x and the variance of y. Okay, so I want to pull these 2's out. So I'm going to pull out the 2 first from the variance because I know how that plays. If I pull this 2 constant out of the variance of x, I need to square it. So we end up with 4 times the variance of x, all of that under the square root. So I'm going to take the square root of that 4. Well, here, I'll write out the steps here. So we've got 4 variance of x times variance of y. Now I'm going to pull this 4 out of the square root. So it becomes 2 times the square root of the variance of x, square root variance of y. Like so. So now I'm going to replace this term with that term just to conserve some space here. So now, pulling out this covariance of x and y. Well, what's covariance? Covariance is the expected value of x and y minus mu x, mu y, right? So I'm plugging in a 2x into this expected value of 2x, y.
Is this what's on top? Or are we just like?
Yeah, this is what's on top. So we're looking at this piece now. Well, the expected value of a constant is just a constant, right? So I can say 2 times the expected value of xy minus these guys. And I dare say, I postulate that mu of x, when we multiply it by 2, will be 2 mu x, right?
Oh, right.
So I'm going to pull a 2 out of this whole thing. And I'm going to say 2 times the expected value of xy minus mu of x, mu of y. Do we agree that this is covariance right here? And that covariance is just being multiplied by 2?
Oh my gosh, this is crazy.
Wait a minute.
Yeah.
Do we agree?
It's true. What the?
So we get 2 times the covariance of x and y over 2 times the square root of the variance of x times variance of y.
Oh my goodness.
The 2's cancel. And what's true is that the correlation between 2x and y is still just rho xy. It's the same as it was before. And this should make intuitive sense to us. Correlation is how the 2 variables move together, right? It's how they impact and influence one another. So if we just multiply one of them by a constant, it's not going to change the relationship between the 2 variables, right? It's a coefficient. It's just going to change the magnitude of things, but it's the change itself, the relationship, the ratio is going to stay the same.
Wait, so now so the answer to the question is actually still false.
Yeah.
Right? Because
Yep.
it's not 2 rho xy.
Yeah, so the answer to this question would be false.
I would have gotten that right on X.
Yeah, I would have just said false because I'd be like, no way, you can't do that.
No chance, illegal. So the one thing of note here, a fun little trick. If you ever see a question like this, you could see it set up like this. You could, they could say like, oh, x 5y equals 5 rho or whatever. any coefficient, it's, you know, if you plug in any coefficient into this, it's just going to end up being rho, with one exception. If I turn this from xy into negative x and y, now it changes the relationship. It flips whatever the relationship was. So this will be the only change that matters. If x becomes negative, or if y becomes negative, or if they just change signs, you know. If x or y changes signs, then it will impact the correlation. But any multiplying by any constant won't impact
To either variable?
to either.
Hold up.
Okay.
Yes,
I've
sir.
got a problem.
Okay,
I don't know if I can explain it in words. Can I explain it?
sure.
What if instead of, and it's this step here. If this was 5, you pull out the 5, there isn't like a good square, because it's just really convenient that the square root of 4 was 2.
Well, but we have to, so we have to square this number coming out of here, right? And then we
Yeah.
take the square root of it.
Okay, just
So as
kidding.
long as this
Never
is an
mind,
even
I'm
number,
back.
yeah, or not an even number, but as long as it's like an integer that's nice and plays nice, then
Okay. Yeah, okay, just kidding.
So the whole formula, the process itself would just keep it regular. That's wild.
yeah. Math is true, guys.
Yeah, no, it makes sense if you do a negative, that's just changing direction. Right?
Yeah.
So, yeah, it's crazy.
Beautiful.
Cool, cool. Any questions? I'm hearing crickets. That's what I'm hearing. Thank you guys for coming.
Thank you.
Nailed that hour and a half timetable. Crazy.
On the dot.
On the dot. I'm something of a professional.